Chapter 7, Section 1, Interference. Now, before starting the interference, we should remember how white light splits into color. The first one is when white light passes through the glass prism, different colors appear, as you see right there. So white light is entering to the prism, and from prism, after passing from the prism, so through the prism, it splits into color from red to violet. This phenomenon is known as diffraction, and this title is studied in the 10th grade physics. However, we can also observe different colors on the surface of a disk or on the surface of the soap bubble. However, the streaks of the colored light coming from a compact disk is not due to diffraction. It is not due to the diffraction, but because of the interference of light. So a new title, Interference of Light. As wave passes through one another, remember we studied this before in chapter 3, they interact to form an interference pattern. So all types of the waves superpose as they pass through one another. So interference is only available for waves. So sound waves, water waves, or earthquake waves, or all can interfere. And anything which has the property of wave makes interference. In this case, if the light is a wave, we should also observe interference phenomenon for light. And if light is wave, so interference phenomena must take place for light and other forms of electromagnetic radiation. If the electromagnetic waves are the waves, we should also observe interference for light and all other electromagnetic waves. So do we observe them? Yes, we do. So the colored light from a disk, as you see here, or a soap bubble, is the result of interference of billions of light waves. So they interfere, billions of the light waves interfere with each other and makes this different color on the surface. However, we cannot study these billions of the waves. That's why we are going to make some controlled experiment. For simplicity, we are going to keep the number of those light waves minimum. So billions of, not billions of the light source, we are going to use only 2 light sources. And also, the light from the source will be monochromatic. What does monochromatic mean? Single wavelength or single colored. Monochromatic. Chromatic is colorful. Monochromatic, single color, not colorful, just one color, single color or single wavelength. So then, providing these two conditions, so we can make a better interference experiment, and we can write its mathematics easily. So in the case of constructive interference, we studied this in the chapter 3, if two waves combine, in the case of constructive interference, crest of one wave overlap the crest of the another one. As you see, crest overlaps to crest, trough overlaps to trough, and trough again trough, and crest again crest. So crest and trough overlap each other. So in this case, we say that the two waves are the two waves have a phase difference of 0 degree, and they are in phase. If they are in phase, so they are crest meets trough meets trough, crest meets crest, trough meets trough, and crest meets crest. So then we say that phase difference is 0. So during constructive interference, a resultant wave is formed with the same wavelength but with a greater amplitude than the amplitude of either waves. Now look at here. This is the first wave. That is the second one. The red one is the second one. So when we add them, so when they interfere, when we superpose these two waves, we get this resultant wave. This resultant wave will have a greater amplitude than the individual waves. Each component of the wave, this one is a greater. So greater amplitude, what does greater amplitude mean? Remember, amplitude determines the energy and the power of a wave. For that reason, if amplitude becomes greater, the result of the constructive interference will be light that is brighter. So greater amplitude in light results a brighter light than the each wave. So this is constructive interference. If constructive interference available, So we can also observe destructive interference. So in the case of destructive interference, so crest of one wave overlap the trough of the other one. So these two cancel each other or weaken each other. In this case, we say that these two waves are out of phase by an angle of 180 degrees. Why? Because these two vectors, if we show them like vectors, they are in opposite directions. If two vectors are in opposite directions, so angle difference between them is 180. And we say that these two waves are out of phase by 180 degrees. So in this case, they are going to weaken one another. The resultant amplitude is less than the larger component of the wave. Now look at here. The first wave is this one. Second wave is the red one, as you see. The resultant wave is smaller than the greater component. As you see, this is smaller in amplitude than greater component. As a result, a dimmer light or dark spot will appear at that point. So, in the case of the constructive interference, a brighter light will be observed. In the case of the destructive interference, a dimmer light or completely dark spot if their amplitudes are equal and then completely they destroy each other. In this case, dark spot appears. So in destructive or constructive interference, energy is not lost or gained, but it is redistributed. What does it mean? Now look at here. Right here you see some interference pattern. Dark, bright, dark, bright, dark, bright, dark, bright. So energy is redistributed. Yani the energy at the dark place is carried to the brighter region, and dark place to brighter region. So total energy of the system is still constant. To form a stable interference pattern, yes, it is easy because it is not easy. But to study the interference and to write its mathematics, we should form a stable interference pattern. So for stable interference pattern, the phases of the individual waves must remain unchanged relative to one another. What does it mean? If they are in phase in the beginning, like this one, as you see, they are in phase. How do we understand? Crest, trough to trough, crest to crest. So at the beginning, if they are in phase, they must stay in phase as time passes. As time passes, as you see, they are in phase, again in phase, again in phase, again in phase. So their phase difference mustn't change as time passes. Or if you are out of phase in the beginning, as you see, this is the crest, this is the trough, they are out of phase, but later also out of phase. This is trough, this is crest, this is crest, this is trough. So as time passes, they are out of phase. So that is why, because they keep their phase constant, so these sources are called coherent sources. So such waves are said to have coherence. Such sources of such waves are said to be coherent. Otherwise, they are called incoherent sources, like this one. Look at here. So these two waves, for example, initially they are in phase because they both have the trough. But as time passes, what happened? Crest of the one of them meets the trough of the other one. It's normal, they are two the same wave. So as time passes, their phase difference is changing. That's why these waves are not coherent. They are incoherent sources. Their phase difference is changing as time passes. So a very usual and common example for incoherent sources is two light bulb. So as you see, these two light bulb results no observable interference pattern even if the light is chromatic. So why? The reason of that is that phase difference between the light waves from two bulbs is not constant. So their phase difference, and they are not coherent sources. So for that reason, you cannot see an observable interference pattern around these two light bulbs. So the light waves still interfere. Yes, there's still interference, but the conditions for interference changes with each phase change. Because the phase change is changing, interference pattern also changing. Therefore, no single interference pattern is observed. So light sources of this type are called incoherent light sources. So two light bulbs have incoherent light sources, or assumed to be incoherent light sources. So, but how can we obtain two coherent light sources? It's not so difficult, in fact. So, light from a single source. This is a single source of light with monochromatic, which is yellow. First pass through a small slit. Slit means a small opening. So as they pass through this opening, they split like this. Right after that, then through two narrow slits, you are going to open two narrow slits to another screen. So through these slits again, light will move. So then on the screen, they are going to form an interface pattern. In this case, S1 and S2 are two light sources which is coherent. So the slits serve as a pair of coherent light sources in this case. So these two S1 and S2, these two slits behaves like two coherent light sources. If monochromatic light is used, your single color light is used, the light from the two slits produce a series of bright and dark parallel bands which is called fringe on a distant screen. So this is the screen. On the screen you are going to observe bright, dark, bright, dark, bright, dark, bright, dark regions on the screen. By why some part is bright, why some part is dark, now we are going to try to understand this. So first assume that a point which is this is the sources S1 and S2. They produce in phase light sources, and they are traveling from these sources to the screen. Right here is a screen on the far from the sources. And first we are going to study the center. Just center between these two lines, these two sources. Assume that is the center. So right here, the waves travel equal distances. Now look at here. This wave and that wave travels equal distances. Thus, they arrive at the center of the screen in phase. Yes, because they are in phase here, when they arrive at the center, also they are in phase. If they are in phase, they are going to result a constructive interference, and they will support one another. You are going to observe the center as bright fringe. So constructive interference appears as a bright fringe. That bright fringe is known as central bright fringe. However, on the screen there are other points. Let's choose this point, for example. This wave travels a longer distance than that one. So as you see here, one of the waves travels a longer distance than the other one for another point on the screen. So if one of the wave has traveled exactly one wavelength farther, as you see, this one traveled one wavelength farther than the other one, the two waves are in phase again. So in this case, they again meet on the screen in phase. Again, they will support one another and result a constructive interference. That point also appears bright area. What if we choose another point on the screen, like here? In this case, this one travels a longer distance than that one, but this time they travel a distance longer than lambda. If this is 2 lambda, if this distance is 3 lambda, 4 lambda, 5 lambda, in this case they are going to meet on the screen as in phase. So if one of the wave has traveled exactly 2 wavelengths farther than the other one, or 3 wavelengths farther than the other one, 4 wavelengths farther than the one, so there will appear another bright fringe. So in this case, one more bright fringe appears on the screen. It is called second bright fringe. So first bright fringe is when the wavelength is this one wave travels a distance to lambda longer than the other one. Second bright fringe appears when the one wave travels at 2 lambda longer than the other one. So this distance between the paths is called as path length difference. If this path length difference is equal to lambda, 0, if it is 0, central bright fringe. If it is lambda, first bright fringe. If it is 2 lambda, second bright fringe. 3 lambda, third bright fringe, and so on. So constructive interference occurs, and thus the bright fringes appear on the screen. So this is the condition for constructive interference. However, if the point is between the central bright fringe and first bright fringe, at that point, just middle, one wave travels lambda over 2 longer than the other one. So if the waves meet midway between the location of the central and first bright fringe, one of the wave travels half a wavelength farther than the other wave. Thus the wave becomes out of phase. Yes, in this case, one of them meets a crest, the other one is trough. Crest and trough, trough and crest and trough, so cancel each other. At that location, the first dark fringe appears because they cancel each other and dark spot appears here. It is the first dark band. So if the waves meet midway between the location of first and second bright fringe, one wave travels 1.5 wavelengths. So if this path length difference is lambda over 2, yani 0.5 lambda, or 1.5 lambda, or 2.5 lambda, or 3.5 lambda, and so on. In this case, there will appear a dark fringe. If the path difference, length difference from the screen to source is 0.5 lambda, first dark. To 1.5 lambda, second dark. 2.5 lambda, third dark. 3.5 lambda, fourth dark. So on. Distracting interference occurs, and thus the dark fringe appears on the screen. So this is the condition, general condition. Now let's make a review. If path length difference is 0, central bright. So if path length difference is 0, central bright. If lambda, first bright. If 2 lambda, second bright. If 3 lambda, third bright. If 4 lambda, fourth bright, and so on. If path length difference is 0.5 lambda, first dark. 1.5 lambda, second dark. 2.5 lambda, third dark. 3.5 lambda, and fourth dark, and so on. It appears on the screen. Okay, so now, but how can we calculate this path length difference? There is a very simple way to find this path length difference. Now, assume that this is the two slits. They are very close to each other, but I'm going to draw these slits further to make understandable. Source 1 S1, source 2 S2. So this is the middle of the sources. Right here is this screen. This screen is in fact very far from the sources. Sources are very close to each other. So right here, let's choose a point on the screen. So the first wave sends a wave, source sends a wave to that point. Second source sends another wave to that point. So in fact, these two sources are so close to each other compared to that distance between the source and the screen. These two waves can be assumed as almost parallel to each other with that one. So all these three are assumed to be parallel, but in fact they are not mathematical. However, because S1 S2 distance is very small compared to L, we can assume that these three waves rays are parallel. In this case, path length difference becomes here. So this distance and that distance are equal. So then this distance will be path length difference. How can we calculate this distance? So this is a right angle triangle, as you see. So D is the distance between two slits. So this is the angle theta, and this is also angle theta. These two angles are the same angles, theta. That is the opposite side of hypotenuse. So opposite side of the angle, which is hypotenuse times sine theta. So path length difference equation is d sine theta. If questions asked to you, what is the equation for path length difference of two double slits? So it is d sine theta. What is d? D is the distance between two slits. Sine theta is the location of the point on the screen. For example, this point can appear bright, dark, according to conditions. If d sine theta is equal to m lambda, it is constructive interference appears, this point appears as bright. But if d sine theta is not m lambda, it is, if it is lambda 0, lambda 2, lambda 3, lambda, and so on, it appears bright. But if path length difference is 0.5 lambda, 1.5 lambda, 2.5 lambda, and so on, it appears right here on the screen dark fringe. Now, I will continue from the text book. So if the distance from the slits to the screen is very large, it's very large, L1 and L2, these rays are almost parallel. The difference in the distance traveled by two waves is called their path length difference, and path length difference is equal to d sine theta, just I proved before. The value for the path difference changes with angle. As you see, as this angle changes, as you see, when you make this angle greater, so in this case, path length difference also increases. So the path length difference determines whether two waves are in phase or out of phase. We did this before when they combine on the screen. If path difference is either 0, remember, or some whole number multiple of wavelength, yani 1 lambda, 2 lambda, 3 lambda, the two waves are in phase and constructive interference results. So it is the condition for bright fringe, yani d sine theta, which is the path length difference, must be equal to lambda, 2 lambda, 3 lambda, 0 lambda, 2 lambda, 3 lambda, and so on. Yani m times lambda, where m can be 0 for central bright fringe, m is equal to 1 for first bright fringe, m is equal to 2 for second bright fringe, m is equal to 3 for third bright, and so on. In this case, so you can calculate the position of that point which appears bright. However, if path difference is not 0, lambda, 1, 2 lambda, 3 lambda, yani if the path length difference is 0.5 lambda, 1.5 lambda, 2.5 lambda, and so on, yani odd multiple of 1 over 2, yani this is 1 over 2 lambda, this is 3 over 2 lambda, this is 5 over 2 lambda. Yeah, as you see, odd multiple of lambda over 2. The two waves arriving at the screen is 180 degree out of phase, giving rise to destructive interference. For that reason, this point appears as dark. So the condition for dark fringe or destructive interference is given by the following equation. D sine theta is equal to m plus 0.5 lambda. So if you are looking for first type dark fringe, you are going to write here 0. So first dark fringe, m is equal to 0. First dark fringe, m is equal to 0. For second dark fringe, m is equal to 1. For third dark fringe, m is equal to 2, and so on. Question. The distance between two slits is 0.03 meters. So what is that distance? This is the distance between two slits is 0.02. D is equal to 0.03 millimeter. Of course, this must be converted to meter. It says that the second order bright fringe is measured on a viewing screen. So second order, m is equal to 2. But it is bright. Yes, it is bright. M is equal to 2. It's bright. Appears on the screen at an angle of 2.15. So theta is equal to 2.15. So determine the wavelength of the light. Calculate lambda. It is constructive interference, bright fringe, because the condition for constructive interference bright fringe is this. D sine theta is equal to m times lambda. Questions calculate lambda. Divide by m. Divide by m. So lambda is equal to d sine theta divided by m. D is 0.03 millimeter. Sine 2.15 divided by 2, result is 5.62 times 10 to the power of negative 4 millimeter. But we should convert it to nanometer. Generally, the question's answer is given nanometer. So, or you can convert it to meter by multiplying 10 to the power of negative 3. So it becomes 5.62 times 10 to the power of negative 7 meter. So if you multiply this by 10 to the power of 9, so you get the as nanometer, which is equal to 562 nanometer. It is the wavelength of the light. So the other questions are very similar to that one. For that reason, I'm just going to pass this. Yes, sectional questions. Let's check the sectional questions. What is the necessary condition for a path length difference between two waves that interfere constructively and destructively? Remember, for constructive interference, path length difference must be lambda 0 for central bright, lambda for first bright, 2 lambda for second bright, 3 lambda for third bright. For destructive interference, yani dark fringe, path length difference must be 0.5 lambda for first dark, so 1.5 lambda for second dark, 2.5 lambda for third dark, and so on. If white light is used instead of monochromatic light to demonstrate interference, how does the interference pattern change? White light contains all the color. So because the sine theta depends on angle, m lambda over d, According to lambda, position of the bright fringes will change. For example, first bright fringe for blue will appear closer to center, but first bright fringe of yellow will appear farther from the center. For that, as you are going to see a rainbow on the screen. Yani white light is split into colors, and that because for maybe at some point first bright of the one color will meet the second bright of the another one. That's why there will be a mixture of the color. That's why it becomes blurred on the screen. Alright, so if the distance between two slits 0.055 millimeter, find the angle between first order and second order bright fringe for yellow light with a wavelength. So sin theta will be calculated. You will calculate sin theta for first order m is equal to 1 and also second order m is equal to 2. So you will find the angle. After that you are going to subtract them. Question number 4. Two radio antennas transmit identical signals with a wavelength of 3.35 meter. A radio several miles away in a car traveling parallel to the straight line. So two antennas, these are two antennas. Distance between them is given as, it's asked to you, distance between them is asked to you. So several miles away there is they are sending the electromagnetic waves whose wavelength is 3.35 meters. So wavelength of the wave is 3.35 meters. Remember, I told at the beginning, the interference is not only for light, for all kinds of electromagnetic waves. A radio several miles away in a car traveling parallel to the straight line between the antennas. So this is the straight line between us. So the car is traveling in that direction. So inside this car there is a radio, and this radio receives the signal. If the second maximum, yani m is equal to 2, and maximum means, for electromagnetic waves we don't write bright because you cannot observe electromagnetic wave, radio means, so that's why we are going to say that it's maximum. So the second order maximum m is equal to 2 appears at a location of 1.28 degree north of the central maximum. So this is the central maximum. North of central maximum, it's 1.28 degrees. So what is the distance d between the antennas? D sin theta is equal to m times lambda is the equation. D must be calculated. Divide by sin theta and sin theta. So then you can calculate the m lambda over sin theta. M is second order. Lambda is 3.25. Sin 128 must be calculated. Answer becomes in this case 300 meters. So the distance between the antennas are 300 meters. Section 2, diffraction. So diffraction is basically explained like this. If a wave changes its direction while it's moving in a medium, or through a small opening or around the sharp edge. So if the direction of the wave changes, so this is called diffraction. So a good example for diffraction is this. You can hear someone who is talking around the corner, but you cannot see the person. This is because sound waves are able to bend around the corners. So sound waves are bending around the corner, so you can hear somebody behind you, but you cannot see that person. So sound waves can bend. Water waves also can bend around obstacles too. Now look at here. Water waves are straight water waves, are coming. So when they reach this opening, pass through this opening, so they start bending, they change their direction, as you see. So they are starting to make a circular wave while they are passing through this opening. Not only water waves, light also bend around obstacles, but because of their short wavelength, the amount they bend is too small to be observed. For example, Jack is from the light reflecting from Jack, and while passing through this opening, it also bends. However, because the the light has a shorter wavelength than sound, it bends very little and you cannot observe the bending. In this case, we can say that if the wavelength of a wave is longer, so you can observe the diffraction better, so or a better diffraction is observed. So this divergence, yani bending of light, not only light, for every kinds of waves from its initial direction of travel is called diffraction. So the bending and change in direction of a wave from its initial direction of travel is called diffraction. So if light does not diffract, you will not be able to observe an interference pattern in a double slit demonstration. So without diffraction, it is not possible to see interference. Instead, you would see two thin bright strips which were lined up perfectly. So there would be no diffraction, so you would see that two bright region on the screen, no more than that. So the rest of the screen would be completely dark. As you see here, this is the light passing through a slit, just one single slit. You see that one part is bright, the rest is, as you see, completely dark, and shadow. So in general, diffraction occurs when wave passes through small openings around obstacles and by sharp edges. Now, we can say that if wavelength is longer, so we observe a better diffraction pattern. But if the opening is small, we observe a better diffraction pattern. So now look at here. This diffraction or this pattern is obtained by an opening whose width is d. But as the width of the opening starts to get smaller, 0.8t, so you see light starting to bend. Now, this is another one. If you do this opening much smaller, narrower as 0.2d, as you see, light starts bending more and more. So we can say that two things determine the bending or diffraction, better diffraction. One of them is longer wavelength. Second one is smaller opening. Smaller opening, longer wavelength. In this case, you are going to observe a better diffraction on the screen, or the wave diffracts more. So when a white slit 1 millimeter or more is placed between a distant source and the screen, light produces a bright rectangle with a clearly marked edge on the screen, as you see this one. But if the slit is narrowed, if you make it narrower and narrower, so light begins to spread out. So as you see, it's starting to spread out and produce a diffraction pattern. If you do it enough narrow, so then you are going to observe on the screen some region, bright, dark region, which is a kind of interference pattern, very similar to interference pattern. So it is because of the diffraction of light while it's passing through a single opening. So how does diffraction take place? The bending of light as it passes through each slit can be understood by using Huygens principle. So what Huygens said, as a wave is passing through an opening, so this is an opening. This is a good example for water waves. So we are going to explain it by light waves too. Huygens said that any point on a wavefront can be treated as a point source of wave. Yani Huygens says that while this wave is passing through this small opening, you can assume that there are billions of tiny wave sources. So each wave source produces its own wave. So these waves combine, you are going to combine these waves and you will get a wavefront. So this small wave is called wavelet. And later you are going to again choose other wave sources here and here. So they will produce their own waves again. So they will travel. So you are going to combine them and you are going to get a later picture of the wave. By this way you can understand why a straight wave becomes circular as it's passing through the small opening. So because each slit serves as a point of source, as you see there are 1, 2, 3, 4, billions of sources through this opening, the waves spread out from the slit. So the waves spread from each source. The result that light deviates from a straight line path and enters the region that would otherwise be shadowed. Normally, we expect light to be travel through this opening, but as you see, light is, or wave is starting to expand more than that opening. So this is called diffraction. According to Huygens principle, now we are going to explain this by light. According to Huygens principle, if you make a small opening on a barrier, very small opening, so as the light is passing through this opening, right here we assume there are billions of tiny light sources, billions of them. So these tiny light sources all are coming from the same source. Because of that, they are in phase while they are passing through this opening, and then they start traveling towards the screen. So if there is a screen on right there on across the opening, so all waves travel to the screen in phase, because at the beginning they are in phase. Because they travel the same distance, all will meet on the screen in phase. So if the waves are in phase on the screen, what does it mean? If the waves are in phase, they will result in constructive interference. That's why the center will appear as a bright fringe. That's why it's called central bright fringe, or another name, central maximum. As you see here, this is the central bright fringe. This fringe is provided or produced by billions of tiny light waves, which is traveling through the screen and making constructive interference on the screen. However, there are more than that sources. There are other points on the screen which can be dark and bright. Like what? Like this. So I'm going to draw the slit a little wider. So I'm going to put there some sources: 1, 2, 3, 4, 5, 6. So I will assume that there are normally billions of sources Huygens set here, but I cannot draw billions of them, so it's hard to do this to make a model by millions of them. That's why I'm going to say put here 1, 2, 3, 4, 5, and 6 sources. Each source produces its own light, and we said that because at the center, because initially they are in phase, at the center, because they travel the same distances, so they arrive on the screen in phase again. That's why center is bright. But if we choose another point right here, so when these waves are traveling through this point and when they meet, as you see, each wave is traveling a different distance, and they are not traveling the same distance like the center. Because of that, some waves are out of phase. If the path length difference between, for example, between 1 and 4, for example, say that this path length difference is lambda over 2. If it is lambda over 2, 1 and 4 will cancel each other on that point, so that point will appear dark. 2 and 5 will cancel each other, appear dark. 3 and 6 will cancel each other, that point appear dark. In which case, if the path length difference is lambda over 2. But so if there are other points right here. So for this point, I'm going to send again waves. The wave from the first one, wave from the second one, wave from the third one, wave from the fourth one, wave from the fifth one, wave from the seventh one. So they meet here at this point. Now, because angle increases, path length difference increases. In this case, in the previous one, 1 and 4 cancelled each other, but now 1 and 3 will cancel each other, 1 and 3, because you increase the path length difference. So in this case, 1 and 3, 2 and 4, 3 and 5 cancels each other, but 6 stays uncancelled. For that reason, the 6th point source right here makes little bright, but it is dimmer than this one. Why? Because 1 and 3 cancelled, 2 and 4 cancelled, pardon, 1 and 3, 2 and 4, 3 and 5 cancelled, but 6, 1 remain uncancelled. For that reason, this uncancelled light makes here a little brighter. If you look at the picture, you are going to see that center is the brightest, because all the sources from this single slit in phase and they form constructive interference. When you move away from the center, number of sources which make constructive interference decreases. That's why we got a dimmer light right there. As you move away more and more, number of sources which is constructive interference decreases, and finally you got dimmer fringe right there compared to the central one. So that's why the central bright, the fringe at the center is the brightest, and this brightest fringe is followed by dimmer to bright fringe. This is called central maximum for that reason, followed by first bright, second bright, third bright, on the left again first bright, second bright, and third bright, and so on. Between two bright fringe appears dark fringe. It is the first dark, second dark, third dark. Also they are known as minima because their light intensities are minimum. So another thing you should be careful is this. As you see, central bright fringe is widest compared to the following bright fringe. In fact, if we say that this width of the following bright fringe is x, central bright fringe is twice as wide as the following bright fringe. There is another thing you have to know about the single slit experiment. So single slit diffraction, as I said, just one opening. We send the light through one opening. So through this opening, we assume, or Huygens assume, that there are billions of tiny light sources each produce its own wave, and they combine on the screen. According to path difference between these sources, screen appears bright, dark, bright, dark, bright, dark, and so on. But when you move away from the center, so brightness of the fringe decreases, and you got a dimmer fringe when you move away from the central bright fringe or central maximum. So this is a single slit diffraction, single slit experiment. Now, we said that diffraction occurs around the edge of all objects. Yes, if the objects are large compared with the wavelength of light, the magnifying glass is required to observe the pattern. Yeah, if the object is small, you get a better diffraction, but if the object is big, you get a less noticeable diffraction. So for that reason, this is a razor blade illuminated by blue light. This blue light, very short wavelength. Also, the razor blade is very big object. That's why you cannot see these lines with the naked eye. For that reason, you should use a magnifying glasses. So as you see here around the razor blade right here, bright, dark, bright, dark, bright, dark regions appear around this. Next one is the diffraction grating. We are going to study diffraction grating. In fact, not so different than the double slit experiment, because in the diffraction grating you make thousands of lines, openings side by side, made like this diffraction grating. So then you think that there are billions of double slits here, or hundreds of or thousands of double slits. So these two, one double slit, this two, another double slit. So that's why these double slits will make an interference pattern on a screen, and point will appear dark or bright according to the path length difference. If path length difference is d sine theta, remember, if d sine theta, it is the path length difference, is multiple number of lambda, you are going to observe on the screen a constructive interference and a bright fringe. So that's why central bright fringe when m is equal to 0. It's very similar to the double slit experiment. So first bright fringe m is equal to 1, second bright fringe m is equal to 2, third bright fringe is equal to m is equal to 3. Why plus minus? Because if this is the central bright fringe or central maximum, right on the right and on the left, you are going to observe first bright fringe and first bright fringe, second bright fringe, or second maximum, third maximum, fourth maximum. You see on the right and on the left of the central maximum, you can see that the first, second, third, fourth, fifth, and so on. The maximum fringe around that, or bright fringe around, about this point. So all waves combine at 0. For example, you send, assume that you send a white light through this diffraction grating. Because all colors, white light contains all the colors, all they combine at central maximum. That's why center appears white. But first, second, third, fourth, fifth, and sixth, these are different for different colors. According to this equation, sine theta is equal to m lambda over d. Because lambda is different, so first maximum for red and blue or orange or yellow, all will have a different angle and their positions will be different. That's why we are going to observe on the screen a spectrum. Yani we are going to observe colors like not completely rainbow, but at different positions you are going to observe that different colors. So that's why diffraction gratings are generally used to split white into its component colors. The sharpness of principal maxima and broad range of dark areas depends on number of lines in the grating. If the number of lines in the grating is big, you are going to get very sharp spot. But if the number of lines in the grating is small, you are going to get a blurred spot on the screen. So the number of lines per unit length in a grating is inverse of the line separation. Why? Assume that a grating is ruled by 5,000 lines in 1 centimeter. So this is assume 1 centimeter length. You are going to draw here 5,000 lines. How can you find the distance between two lines? You are going to divide this 1 centimeter by number of lines. That's why slit separation or line separation will be equal to 1 over 5,000 centimeter. So if there is 5,000 lines in 1 centimeter, slit separation will be 1 centimeter divided by 5,000 lines. Now, diffraction gratings, as I said, are frequently used in devices called spectrometers, which separates the light from a source into its monochromatic components. So this is a very good example. As you see, this is the spectrum of a light coming from a gas. So it's shifting from red to violet. So we can understand what kind of gas is this by searching its spectrum. So the spectrometers are extensively used in astronomy to study the chemical compositions and temperatures of stars or interstellar gas clouds or galaxies. So we can understand what kind of gas exists in the stars or the galaxies or in the space by studying the light coming from those objects. Sample problem 7b. Monochromatic light. What does it mean, monochromatic? Single color or one wavelength. So monochromatic light from a helium neon laser, lambda is equal to 632.8 nanometer, it's the wavelength of the light, shines at right angle to the surface of a diffraction grating that contains 150,500 lines in 1 meter. Find the angles at which one would observe the first order and second order maxima. So for first order maxima, you are going to write m is equal to 1. For second order maxima, you are going to write m is equal to 2. Maxima means constructive interference, bright fringe. So you are going to write the condition for bright fringe, d sine theta is equal to m times lambda. Sine theta is equal to m lambda over d. This is your equation for finding the angle at which the first or fringe appears. So d must be calculated. Remember, we said that if 150,500 lines in 1 centimeter, to calculate this slit separation, you will divide 1 meter to 150,500. So that's why if you do this calculation, you will find the line spacing or slit separation by 6.64 times 10 to the power negative 6 meters. So right after that, you are going to write the numbers here. For m is equal to 1, first calculate. M is equal to 1. So lambda is 632.8, almost 633 times 10 to the power negative 7. So slit separation is, or line spacing is 6.64 times 10 to the power negative 6. When you do this calculation, you will find the position of the first bright fringe. For second bright fringe, you are going to write m is equal to 2. So when you write m is equal to 2, you will get the position of the second bright fringe is almost 11 degrees. So almost 545 multiplied by 2 is the 11. So a diffraction grating, but these are very similar questions. That's why I'm going to pass this. I'm going to solve some questions with different. Which one is different? Now let's solve this one. A grating with 1555 lines per centimeter is illuminated by a light of wavelength 565. What is the highest order number that can be observed with this grating? Remember, sin theta can never be greater than 1 for diffraction grating. So first we should find the line spacing. How can we find line spacing? In 1 centimeter there is 1555 lines. But 1 centimeter, but when we make calculation we should convert it to meter. How? 1 centimeter is equal to 0.01 meter. So divided by number of lines, 1555, line spacing will be 6.643 times 10 to the power negative 6 meter. Now we know and d sin theta is equal to m times lambda. Sin theta is equal to m lambda over d. So for maximum number, highest order number of maximum, so you should make sin theta maximum 1. If sin theta is it must be smaller than 1, sorry. So if sin theta is smaller than 1, m lambda over d also must be smaller than 1. So you are looking for maximum m. M must be smaller than, in this case, d divided by lambda. D is calculated 6.423 times 10 to the power negative 6. Lambda is given in the question as 565. So it's 0.565 times 10 to the power negative 6. So when you do this, you are going to observe m is smaller than 11.4. So the smallest integer, because m is integer number 1, 2, 3, 4, 5, 6, 7, and like this, so on. The smallest integer than the closest integer, not smaller, closest, smallest and smaller and closest integer than 11.4 is 11. So you can observe on this diffraction grating highest order number as 11. So another question, a diffraction grating is calibrated by using 546.1 nanometer line of mercury vapor. The first order maximum, yani m is equal to 1, its maximum found at an angle of 21.2 degrees. So theta is 21.2. Calculate the number of lines per centimeter. So d sin theta is equal to m times lambda. D is equal to m lambda over sin theta. Why we should calculate d? Because from d I will calculate number of lines. Initially we did, if the number of lines is given, 1 over d is the 1 over n is equal to slit separation. But this time I'm going to calculate first slit separation, then I'm going to do it 1 over slit separation, which will give us the number of lines in centimeter. First, let's get the line spacing, m lambda over sin theta. M is 1, lambda is given 546 times 10 to the power negative 9, so nanometer must be converted to meter, divided by sine of 21.2, so answer is 1.51 times 10 to the power negative 6 meter. But question is asking per centimeter, that's why I should convert to meter to centimeter. So 1.51 times 10 to the power negative 3 centimeter is the line spacing. Then if d is equal to 1 over n, n must be equal to 1 over d. So 1 over d, d is 1.51 times 10 to the power negative 3. So you will get the answer as 6,622 lines per centimeter. So this is the answer of the question. Okay, conceptual challenge questions. Photographs of stars always show spikes extending from the stars. Given that the aperture of camera's rectangular shutter has straight edges, explain how diffraction accounts for spikes. Remember, while the light is passing through the sharp objects, around this sharp object, even if we cannot see with our eyes, there will be bright, dark regions. That bright, dark regions and diffraction is the cause of those spikes. Visible light waves are not observed diffracting around buildings. Yes, when you look at around the building, you cannot see light is diffracting. other obstacles. But however, radio waves can be detected around buildings or mountains, even when the transmitter is not visible. So you can listen radio everywhere, even if your radio does not face the transmitter. So explain why diffraction is more evident for radio waves than for the visible light. Because radio waves have a longer wavelength. If the wavelength is longer, diffraction is more noticeable. If wavelength is shorter, diffraction is less noticeable. Okay, so these are the questions. Sectional questions, the rest are very similar to the previous one. That's why I'm going to pass this. Question number 2. It says, describe the change in the width of central maximum of a single slit diffraction pattern as the width of the slit made smaller. As I explained, two things makes a noticeable diffraction. Longer wavelength is one of them. Second one is narrower slit. If you make this slit narrower and narrower, so in this case, better diffraction will be observed. That's why width of the central maximum will increase. So because the light will spread out more. Question number 3. Which object would produce the most distinct diffraction pattern? An apple, a pencil lead, a human hair. Human hair, because remember, size of the object must be smaller. If the size of the object is smaller or opening is smaller or narrower, in this case you are going to observe a better diffraction pattern. Would orange light or blue light produce a wider diffraction pattern? So the one which is longer wavelength will spread out more. I mean, it will deflect more. For that reason, orange light will deflect more and we will see a better diffraction pattern on the screen. Okay, so next section, I'm going to combine this section with the laser. Section 3. When electric charges move through the filament of the typical light bulb, electromagnetic waves are emitted in the form of visible light. As you see, there are so many waves are leaving from the bulb. However, these electromagnetic waves emitted at different times, yes, from different parts of the filament, and have different intensities. Even they move in different directions, include light of different wavelengths. That's why this light is assumed to be not incoherent. For that reason, light produced by the bulb is incoherent, and they therefore do not produce a stable interference pattern. So remember, it was one of the conditions to produce a stable interference pattern to be coherent, sources to be coherent. But all these sources are not coherent, they are not moving in the same direction, they don't have the same intensities, and all they move in different directions and different wavelengths or so on. However, lasers produce a narrow beam of coherent light. So laser means coherent light. Because all waves are in phase, yes, coherence is not enough, also must be in phase. They interfere constructively at all points, as you see here. All waves are in phase. As time passes, their phase difference is not changing and so coherent. So they will support each other and result a greater amplitude. The light produced by a laser is monochromatic because they have single wavelength. As a result of this constructive interference, the intensity of the laser is much greater than incoherent light. So a laser is a device that converts electrical energy, chemical energy into coherent light. So it is the definition of laser. So there are different types of lasers, but they all use a substance called active medium. What is active medium? The medium to which energy is added to produce light of coherent light. Active medium can be a solid, liquid, or gas, but generally gas is used more practically. The composition of the active medium determines wavelengths or color of the light. Yani, what kind of atom is used in the active medium, so determines the wavelength and color of that light. So how does the laser formed? When electrical or chemical energy is added to the active medium, the atoms in active medium absorb some of the energy and excites to higher energy levels. So remember, this is the normal chapter 8 title. When you give normal atoms are electrons of an atom stays in ground state. But when you give energy to the atoms, electrons excite to higher energy levels. In an atom, there are so many energy levels, all have different energies. So when you give energy to the atoms, electron of atoms excites to higher energy levels, but we cannot control that. So electrons can excite to different energy levels. But these electrons does not stay there. They transit to the ground state. This is the ground state. Stays there. As they are transiting from the transmission from the higher energy level to ground state, they give different color of light. So this is not a coherent. This is not a coherent light. This is not monochromatic. So the transition is called spontaneous emission. So this does not make a laser. This part is not explained in your book. Normally, how laser is produced. To produce a laser, generally they put the level which is known as metastable state. Metastable state. Right below the second energy level, between the ground state and the following energy level, metastable state. So when this state is located, excited electrons all transit to the metastable state. So normally, it is somehow we deceive the electrons. They think they come to the ground state because right after this energy level, right there is the ground state. So all the atoms, all the electrons collide here and stay there for a long time. For a short time, but not so short compared to the previous one, spontaneous emission. Right after that, you send a photon whose energy is exactly the same or energy of this interval. So this photon sent by you stimulates, stimulated emission, stimulates this electron, and this electron transits from this metastable state to the ground state and emits an identical photon. So these two photons stimulates two more electrons. They transits to the ground state and release two more photons. So number of photon increase becomes 4. These 4 stimulates other 4 electrons and number of photons increases and becomes 8. 8 stimulates 8 becomes 16. 16 stimulates 16 becomes 32. So by this way, number of electrons, number of photons in the active medium increases. 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, 16 becomes 32. So in a very short time, number of photons, identical photons with the same color, one directional and coherent increases. This process is known as stimulated emission. So laser is obtained by stimulated emission. However, as these photons are moving through the active medium, so number of photons increases. But right here, put 2 mirrors. What is the function of these 2 mirrors? These 2 mirrors reflects the photons back into active medium again. Because while the photons are moving through the active medium back and forth, number of photons, the intensity of the light increases. When the light has enough intensity, one of the mirrors, partial reflection mirror, allows the laser to leave the medium and appears as a laser beam. So, function of these mirrors is to reflect the photons back into the active medium and to produce more identical photons. And when these photons have enough intensity, they are going to leave the active medium from this partial reflection mirror. Yes, one mirror is partial reflection, one mirror is total reflection. That's why we get a much stronger light than the incoherent light or light from above. So this phase is known as light amplification of stimulated emission of radiation. So light amplification, stimulated emission of radiation, so laser. Amplification means increasing the power. Stimulated emission is the method which we get the identical photons from just one single photon. So generally these lasers are using electromagnetic waves till the X-rays. However, some lasers are using microwaves. They are called masers. So masers are also operating with the same principle of laser, but only they use an electromagnetic wave which is in the region of microwaves. Lasers are used in many places. Lasers can be used to measure large distances because they are traveling in one direction. Lasers can measure distance with great precision. Geologists use repeated measurements to record the changes in the height of the Earth's crust. Lasers improve information storage or retrieval. Remember, CD player, DVD player, all uses laser. Lasers can be used to lighten or remove scars or certain types of bird marks without affecting surrounding tissues because you can directly send the laser to that point. Carbon dioxide lasers can cut through muscle tissues by heating and evaporating the water contained in the cells. The energy from a laser also coagulate blood in a newly opened blood vessel, so thereby reducing the blood loss and decreasing the risk of infection. So coagulating blood most probably increase evaporating the water inside the blood and then stopping the bleeding. A laser beam can also be trapped in an optical fiber endoscope, which can be inserted and directed into internal body structure. As a result, surgeons can stop internal bleeding and remove tumors without affecting massive surgery. So without cutting the body, so you can insert the optical fiber endoscope, which is inside through which laser light is moving, so then you can search inside the body. Lasers can pass through the outer structure of the eye, such as the cornea and lens, without damaging them. Therefore, lasers are effective at treating lesions in your eye. Lasers are used for other eye surgeries, including surgery to correct glaucoma, a condition in which fluid pressure within the eye is too great. As you see, lasers are very important devices used especially in medical science. So those are some titles in which lasers are used. So section of questions: how does light from a laser differ from light whose waves all have the same value but not coherent? If not coherent, they will not constructively interfere. So in the laser, because they are coherent and in phase, the waves will constructively interfere and increase the intensity of the light. The process of stimulated emission involves producing a second wave that is identical to the first one. Remember, one photon is sent and then becomes 2 photons, 2 becomes 4, 4 becomes 8. So does this gain of the second wave violate the principle of energy conservation? Explain your answer. It is not violating because this energy is given to the extreme medium initially by other sources like electrical energy or chemical energy. Fiber optic systems transmit light by means of internal refraction within thin strands of extremely pure glass. In these fiber optic systems, laser light is used instead of white light to transmit signal. Apply your knowledge of refraction to explain why. So first we should remember what internal reflection is. So while light is coming from a glass to the air, so this is the air region, this is the glass region. So while light is coming from glass to air, if it comes with an angle greater than some critical angle, so it reflects back. But this angle depends on two things. One of them is the medium glass. Second one is the color of the light. So for different for different color of the light, this angle is different. If you use single color, you can easily calculate at what angle it will reflect, and by this way you can transmit the signal without leaving this pure glass. But if you use white light contains many colors. So some colors can leave out the pure glass, but maybe one of them is traveling, but this others are leaving. For that reason, you cannot transfer the signal through this glass by using white light.